Welcome to lecture number 27 of the Statistical Thermodynamics course. So let us see. So in this lecture, we are going to cover how the electronic energies or the electronic energy levels, okay, and degeneracies of atoms can be typically written for a multi-electron kind of a system. Okay, so let us look at so we are going to take a look at the corresponding definitions and how this can be best written. So in the previous class also we provided quite a bit of information that how the term symbols can be written. Here the electronic energies for multi-electron atom can be obtained, right? Can be obtained by spectroscopic methods. By spectroscopy. This we already told earlier that it is developed from spectroscopy. So typically excitation above the ground electronic state occurs due to chemical or radiative processes that excites a single valence electron to a more energetic subshell, right? So what happens is that excitation above the ground electronic state is usually determined by by chemical or radiative process, chemical/radiative process. What it does is that it takes a valence electron and promotes it to a more energetic subshell, right? Now we already know that each energy level, let's take each energy level. Now those energy levels are designated by the configuration part is designated by N, L, etc. This is the configuration part, the atomic configuration. That's why we know the 2s2, 2p6 and stuff like that. And then we have the term symbol, which takes into account the interactions, which is L, S, and J. So the term symbol and the electronic energy, so those are kind of can be listed. So similar for simple elements, which is below z equal to 40, okay, below z equal to 40, can be written in this particular form. So let's take z equal to 19, which is basically nothing but potassium. So let us look at how the energy actually looks like. So the energy for potassium is written in this particular fashion. So these are the energy levels and the associated degeneracies for atomic potassium. So as you can see that the configuration when it is that is the argon configuration and 4s, the term symbol is written as 2s half, okay, and so this is the effective degeneracy is given by 2. We will come to the point that what is actually called effective degeneracy in just a little bit. So similarly, when you look at the other configuration, the electronic energies of potassium, so these are the electronic energy levels of potassium level diagram, right? So and then each energy level, as we can see, is provided by both the configuration, which is N and L, and the term symbols, which provides L, S, and J. So that's why you have a doublet state here, okay, with a degeneracy of 6. And then, so these are the different energy levels. And if you look at the diagram, on the right-hand side, okay, if you look at the diagram, This is also portrayed by the allowable transitions over here. So the transition part also, you can see that the allowable transitions that can happen. So this is basically the energy diagram. This is basically the corresponding figure which shows which is a more graphical description, and it also indicates the allowed energy transitions, including the wavelengths of the resultant spectral lines. So that is what is actually given in angstroms. If you look at the units, they are given in angstroms. Okay, so the intense, you can see a few things. There are some intense resonance lines at 7665 and 7699. Okay, these are observed even at very low potassium concentrations, 7655 and 7699. These are the resonant, these are the two resonant lines that are readily available. Okay, so you can see there, okay? You can see a couple of them. Okay, especially here. So if you look at the lower part, here you can see the lines. Okay, and so that is a couple of lines which is of interest. Okay, so much can be learned between this, the relationship between these electronic energy levels and the atomic spectroscopy. Okay, the relationship between the two. Okay, so also figure 6.8 indicates that potassium is, is characterized by doublets. Okay, there is a lot of doublets, as you can see over there. Just look at the term symbol, you will get an idea that there are a lot of doublets. Typical spectral features of other atoms, however, can include triplets, quartets, quintets, and septets. So in fact, so these are quite possible, and we will see what the effective degeneracy is. This is something that we have not covered so far. We will do that in a minute. But as you can see, potassium, this is a typical energy level diagram for potassium. And this indicates that what are the allowable energy levels and what are the allowable energy transitions that you can have. As a result of that, you can also construct diagrams in which you can see which are the allowable energy levels as well. So that is an important feature of this particular thing. Okay, so just writing down a few things. Okay, so you can see intense resonance lines at 7665 angstrom and 7699 angstrom. Okay, even at low potassium concentrations, these lines are available. Okay, so now let us look at what is meant by effective degeneracy. Now we already know that GEL is equal to GJ is equal to 2J plus 1. Okay, so this is something that we already know. So the electronic degeneracy can be effectively calculated from the J values, right? So the electronic degeneracy can be effectively calculated from J values, right? J values. However, if you recall the table that I just showed, the shifts in energy levels. So the shift in energy among levels, okay, with only changes in J, okay, are usually very small. This is also given in the table that you can just now see, that the change in the value of the energies, because it is like, for example, 2154.37, 2153.7. Okay, so this variation in energy is very, very low in the case of when there is only changes in J. Okay, if you don't recall this, let's just go back to the diagram. As you can see over here, look at the doublet state, P1, 2, and P3, 2, or look at D 3 by 2 and 5 by 2. As you can see, the change in energy is very, very low. For example, it's 3 in the case of this D, 3 by 2, 5 by 2. So as you can see, so therefore, what we have written over here, that the shift in energy among levels with only changes in J is usually very small, very, very small. Okay, so small that we can define an average. We can define an average energy because the differential is very small, and thus an effective degeneracy okay, corresponding to all J values, okay, with same L and S. Okay, so GL effective is basically sum over all J, GJ, which is basically J equal to sum over J, 2J plus 1. Correct? So it is just summed over all the things. So in the same way, so you can understand the corresponding to all J values, okay, with the same L and S. Remember, with the same L and S, that is mandated. So those two, once they are kept the same, we can define an average energy, which is basically the average energy of among the different J values, and an effective degeneracy, which corresponds to all the J values for the same L and S. And this is how you calculate the effective degeneracy. Okay, you calculate the effective degeneracy. Okay, so in some cases when the J value is just 1, so it is basically you can make an estimate that what will be the effective degeneracies in those kind of cases. Okay, so in this case, so let us look at the figure once again, because I think that will give us a better idea. So let's take a look at the degeneracy of the first term, which is given as 2, right? So the J value is half. So 2 into half is 1 plus 1, which is basically gives you 2. Let's look at the second one, which is half and 3 by 2. These are the two J values. So 2 into J, so that is basically, and we are summing over all J, remember, we are summing over all J. So you can put half, so it is once again, that is the same, it's 2, and then you have the other J value also, right? So which is basically 2 into 3 by 2, which is 3. So 2, 1 plus 3 plus 2, so that gives you the 6. So this is how you can calculate the effective degeneracies among the multiple levels. Okay, so the number of J values, for given values of L and S is called multiplicity. Okay, called multiplicity. Okay, in most cases, differing J values, or the number of J values, or the different J values, okay, gives rise to closely spaced lines in the spectrum, okay, which is something that you saw in the figure. Okay, so as we can, so different J values, and which together, these closely spaced lines together forms forms what we call multiplet. So this is now, you can understand that potassium shows lots of doublets. Similarly, there can be other atoms or molecules which can show other kind of symbols as well. Okay, so this is the first thing, okay, that we have done. So we now know that what is effective degeneracy, what are the kind of transitions that are allowed, right? And how to, so a particular atom in a multi-electron kind of a system is specified not just by the electronic configuration, but also by the term symbol, right? So these two are important. So next what we do is that we now look at the the degeneracies or the electronic energies. So electronic energy levels and degeneracies for diatomic molecules. All right, okay. Now, diatomic molecule is a little bit different. Okay, so all molecules exhibit, so let's write all molecules, okay, exhibit okay, suitable orbital and spin angular momentum vectors. Vectors L and S, momentum vectors L and S. Okay, however, so it exhibits that kind of a vector. So suitable orbital angular momentum vectors L and S. However, for a diatomic molecule, okay, only the components of L and S, okay, along the internuclear axis, undergo quantization. This is primarily due to the cylindrical rather than spherically symmetric electronic potential. Due to cylindrical electronic potential. Okay, so if we look at now a simple figure, so this is going to tell, so this is say A, this is say B, these are the two atoms. This is their internuclear distance, A and B. Okay, and they say this is your L. Okay, and this is your S. Okay, so we are going to take electrons along this internuclear axis. Okay, so when this is processing, or this is the part, this is written as gamma. So you can read it as sigma. Okay, and so this is omega. So these are the Greek symbols. Okay, so this is how this is written primarily. Okay, so your LAB, okay, is plus minus gamma h bar. Gamma is equal to 0, 1, 2, da da da. SAP, which is the spin, is given as summation, or basically sigma h bar, so not summation, minus s plus 1 continued s minus 1 S. Okay. So sorry, this I perhaps drew it as L. It's not L. This is your S. Right. All right. So the plus minus term that you see over here, this represents clockwise or anti-clockwise, clockwise or anti-clockwise, clockwise, rotation or circulation of electrons about the internuclear axis. Internuclear axis, not present in the case of spin. Okay, so this is the component of orbital angular momentum. Orbital angular momentum about the axis AB, which I drew in this particular figure, AB along this axis. Okay, so similarly in equation, in the equation for S that we wrote, for every value of spin quantum number, for every value of spin quantum number, here we have S plus 1 values for its component along the internuclear axis. Okay, so we recognize that L and S, okay, must precess about this axis. Okay, similar to J. In multi-electron atoms. So J for multi-electron atoms. This is L and S. They precess about the internuclear axis. So for a molecule, okay, the electronic energy, electronic, okay, depends on the quantum numbers, depends on these two quantum numbers. This is very similar to the L. This is similar to L and S secondary dependence for an atom. Okay, so therefore the molecular term symbol is 2s plus 1 omega. So this is 0, 1, 2. Okay, represented by, this is correctly represented by summation pi delta, etc. Okay, the subscript omega is equal to sum total of these two, is basically appended to identify spin component, particular spin component, similar to J for atomic systems, similar to J for atomic systems. For all molecules, okay, multiplicity is defined by 2s plus 1. Okay, like, and in like the atomic case, now similar to the atomic case, similar to atomic case where spin orbit coupling is usually small, okay, enough. So we can define very similarly an effective degeneracy, which is given as GEL effective is phi into 2s plus 1. Okay, so where phi is equal to 1 for gamma equal to 0 and phi equal to 2 for greater than 0. Thus accounting for this basically accounts for the two possible vector directions along the internuclear axis. So this accounts for two different vector directions along the internuclear axis when LAB is greater than 0. These two factors, this factor of 2 okay, is called the gamma W. Okay, and 2s plus 1 is called spin splitting. Okay, the degeneracy therefore is the degeneracy that is defined GL effective phi into 2s plus 1, okay, is clearly effective, clearly effective as spin splitting and gamma doubling. Okay, so this leads to spectral lines, okay, having slightly different wavelengths, okay, although the energy difference, but however, one thing that you should note here, that the energy difference okay, due to gamma doubling is smaller than spin splitting. Okay, all right. So this is akin to the atomic case. So the electronic energies for diatomic molecules are also typically derived from the spectroscopic measurements, which we will cover in more details a little later. But these are the different term symbols, and these are the different significances. These are the different degeneracy values that we have got out of this exercise. So next we will look at something which is a little bit more interesting. We'll look at the combined energy modes for atoms and diatomic molecules. But before that, we are also going to look at the typical electronic energy levels for oxygen, say, for example. So that we will do in the next class.